So the literate programmer, so first just a little background on what this idea is. So I think it's important for programmers to be literate in that they've like read the classics or like know history in the same way that it's important for people, for citizens to have like a shared culture and base to work from. So like to this end, I've been pulling together thoughts about computing and history, in particular with respect to the technology that I use. I don't have a SoundCloud, but I do have a tiny letter, so I like write these things out every so often. So before we start, actually, I wanted to see if I could compute the median age of the audience here. So if you are under 30, raise your hand. Oh, is that about half? Was that actually the median? All right, I'm just going to claim it's the median. Okay, so that means that you started your career probably around 2008, and the stuff that I'm going to be talking about primarily centers before 2008, and then kind of goes a little bit past that. So it might be some things that you haven't heard of before. Okay. How do I go to the next slide? Oh, the clicker. Aha! Oh, that's fanciness. All right. I can't figure this one out either. Who writes computer programs for a living here? Okay, there we go. Okay, cool. All right. Okay, so I'd like to start the talk here. So this is Paul Henningkamp. So he's done several notable things. He's well known in the FreeBSD community, and he's like built technology that has probably touched you in ways that you don't even realize, even if you're not a FreeBSD user. So he's done many things, but I'd like to sort of call out three things, and then I'll go into depth on one of them. So first is that he and Rob Watson came up with FreeBSD jails. So this is the first widely used container implementation, and this was sometime around 2000. Solaris followed with zones in 2005. Linux C groups, which is a predecessor to containers in Docker, was in 2007, and then Docker itself was in 2013. So this is 13 years. Docker came 13 years after jails. And using FreeBSD jails, there were actually companies that would allow you to rent slices of computing time. That was before Linode and Zen, and that was before Amazon EC2. Second thing is he invented the term bike shedding. And it means a cacophony of opinions that surround the most trivial of proposals. The basic idea here is that the more trivial something is, the more likely someone knows something about it, and then so the more likely that they'll come up with some argument or have an opinion. But he said, we need a bike shed, it doesn't matter what color. And the final thing is this, Varnish. So this is probably a thing that everyone here has heard of or had to deal with at some point. So this is a reverse caching proxy. So what is a reverse caching proxy? I always thought that this was kind of a funny name because it's relative sort of to your point of view. But in the olden days, companies would have to run these proxy systems. So every request that started internally inside of a company's network would have to pass through some machine. And so this was for performance and security reasons. They called this machine a proxy. So that was always like it was this intermediate step that the request had to move through to leave the office. Now, a reverse proxy is the opposite of this. The requests start from outside of the network and come in. And so this is the form of proxy that you probably know about, and this is the form that Varnish takes on. In the old days, there's this thing called Squid. I'm guessing most people here have probably not used Squid, but it was immensely popular. Yeah, raise your hand if you use Squid. Okay, so like let's say less than a tenth of the people here, right? So it was first written as a proxy. So it took requests that came from inside of the network going out. And then they threw in some features. They threw in caching. So if people were asking for the same request over and over again, then Squid would just return that. And Squid could also mess with headers and stuff. So it was like a nice piece of software. But because Squid caches these requests, it had to keep track of what memory it was using very carefully, and it had to know, because in these days systems didn't have a lot of memory, it had to know when to move these objects from disk into memory and back. because it had these features, they figured, okay, we can also make this thing a reverse proxy, right? So requests coming from the outside will just use a lot of the same code. So, so this is great for performance. Someone from the outside is asking for an object inside of your system. You don't want to be contacting your web server over and over again. You just have Squid respond for you. So this is where Varnish comes in. So PHK's Varnish caching reverse proxy competes with Squid just for the reverse proxying use case. So he looked at the design of Squid, right? And he looked at how Squid was messing with all the memory, and he thought, all this logic is actually it's actually done inside of the OS. So why should we have it in the application as well? And so he wrote this 1975 programming is a very opinionated essay. We'll come back to that in a sec. Okay, so what did he mean by the operating system just doing all the logic that Squid's doing? Okay, so if you use a high-level language like Python or Ruby or Java, you're accustomed to thinking about memory allocation in terms of object allocation, right? So you say, okay, I need enough memory to hold an instance of class X. Okay, if you go down one level of abstraction, you'll find that these objects are actually represented by contiguous arrays of bytes. So in C land, you don't ask for these objects, but instead you ask for multiple chunks of contiguous bytes of possibly different sizes. And so it turns out, so RAM in a computer is essentially a single big array of bytes. And so the question is, okay, how do you get from the application asking for a small chunk of bytes to carving it out from RAM? It's bad when you have several programs that are trying to run simultaneously, right? So you don't, wait, did I just like skip a, hold on. Sorry, okay, yeah, sorry. So how do you carve these bytes out from RAM? Okay, so in the old days, what would happen is that programs would share the same address space, right? So this meant that the computer knows what RAM it's got, and it can be accessed as bytes, let's say 0 through 65,000. And when a program runs, it can start reading and writing memory wherever it wants. And so this is fine if there's a single program on a single machine. And if you want to program in embedded systems like the Arduino, this is still something that happens. But it's bad when there are multiple programs that are trying to access RAM at the same time. So you would like to protect these programs from each other. So imagine that you've got this array of bytes and you have two programs that start up, and suppose you can allocate some bytes to one program and some bytes to another. So program A says, I want 800 bytes, and the operating system says, okay, great. You can take bytes 0 through 799. And the B says, I want 1,000 bytes, and the OS says, great. You can take bytes 800 through 1799. And A again comes back and says, okay, I now need 30 more bytes, and the OS says, okay, great, take 1800 to 1829. So now what we have is application A owns bytes 0 through 799 and 1800 through 1829, and then B owns 800 through 1799. But how do these programs figure out like which bytes are theirs? Like how do they keep track of this? Like what does that kind of a structure looks like? And then what happens when program A releases 0 through 799 and then tries to access it again, right? Like how do you keep track of these free chunks? And then what happens if program A actually tries to access B's memory? So how does the operating system know? So there are lots and lots of questions here. So what happened was in the mid 80s, we invented another layer of abstraction called virtual addressing, and with some help from the CPU, some hardware support, we just totally swept this mess out of the room. So in the Intel line of processors, this happened around the 386. And so with virtual addressing, what happens is that we change the way that programs understand their memory. So previously, two programs might share the same sort of array of bytes, the same physical array of bytes, but now with virtual addressing, they're both assigned to seemingly infinite sequences of bytes that both start at 0. So both programs have arrays of memory that start at 0. But what if two programs want to access the thing that's at 0? So if we don't want those two bytes to actually be the same physical bytes. And so what virtual addressing says is the OS will keep track of mapping program A's byte 0 to a physical address, say byte 4096 in RAM, and then program B's 0 index to a different physical address, let's say byte 8192. So with this in place, it means that we can perform some neat tricks. So first, the tracking of which chunks of memory a program goes to has become a problem of the OS and not of the application. So this simplifies the application, since it could just assume that it's got this, this straight up space starting at 0 and stretching to infinity. And then the OS doesn't have to assign a mapping from one virtual address to RAM until it's actually needed. And then the third thing is that a virtual address doesn't even have to point to a location in memory. So this is super cool, right? It could point to some location somewhere else, like on disk, right? So that's swap, or even on some machine that's connected by a network. So having this stuff on disk is neat, but accessing a byte off of disk is really, really slow compared to memory. And of course, the network is even slower. So this is a pretty famous table. I think this Peter Norvig wrote this years ago. It's on his website somewhere. So you can see, third from the bottom is the time to fetch a new disk, fetch from new disk location is seek. So that's 8 milliseconds. These days, rotational hard drives are, I think, around 3 milliseconds, and then an SSD is around 0.1 milliseconds. So, so these numbers aren't entirely accurate, right? But this is, that's the gist of it. And if you look at, where is it? Fetch from main memory, so 1, 2, 3, 4, 5, 6 from the top, it's 100 nanoseconds. So pulling data from disk is 4 orders of magnitude slower than from memory. So it's a really, really big deal. Right? So you can kind of trick the program into thinking that it has more RAM than it does, but programs aren't expecting the access to RAM to be as slow as disk. So the OS has to do this kind of a tricky thing of taking bytes on disk and then migrating them into memory and creating a new mapping behind the program's back. There's some tricks for optimizing this. It can, for instance, do this in bulk so that the sort of average times for moving, for accessing something that's a disk isn't so bad. Right? That's called paging, and we'll talk more about that. All right. So in C land, you're allowed to ask for arbitrary sized chunks of memory. So imagine over the course of a long running program, right, you may ask for chunks of different sizes, free them up, ask for more chunks of the same sizes or different sizes, and over time your memory starts to look like Swiss cheese with holes in it like this. So like burn this into your brain because this will actually become important later. Sometimes programs don't have to ask for lots of arbitrary sizes of memory. So suppose, for instance, you have a 3D flight simulator, and you've got a lot of instances of a type called point, and a point consists of XYZ floating point coordinates. So all of these things are the same size, so you might imagine you could write some kind of a specialized memory allocator that's really optimized for points, if you have a precise definition of what a point is. So this is domain knowledge that the operating system doesn't have. So we need to be able to push this kind of memory allocation logic into the app. But what is the OS supposed to do when the app asks for something as specific as like 27 bytes of memory? So the trick here is actually that the app is not allowed to ask for 27 bytes of memory. Instead, what the app does is it asks for entire pages of memory. So a page is basically a fixed size array of bytes and is usually something around 4K. So the program says, okay, I need a page of RAM. The OS says, sure, here it is, go nuts. And then it's up to the program to figure out how to split that 4K into 27 byte chunks or whatever size it needs. So how a program decides to carve that up is a subject for a different talk. These things are called memory allocators, and there are lots of different versions. It's not well known, but in a C program in Unix, you can actually replace these allocators, which is cool. You can pick different allocators for different performance characteristics. So the OS doesn't deal with these arbitrary chunks of data. Instead, it just deals with pages. And this is a much easier bookkeeping problem. So it can just keep a list of free pages and pages that it's assigned to apps. It can take these pages and, like I mentioned before, it can migrate them onto disk when they're not being accessed, and it can bring them back into memory when it thinks that it needs them. The OS can also it can guess when it's safe to eject some page from RAM to disk, and when it might want to prefetch some page from disk into RAM. And so that, in a sense, is the Squid problem, right? We need to make guesses as to which objects in Squid or pages in the OS are frequently accessed to make sure those things stay in fast RAM. So another thing of note is that the APIs that RAM and disk exposed to the OS are in pages, in terms of pages anyways. So it gets to pass through some of the access logic and also gets special hardware support around pages. So like for instance, the CPU can tell a program, if can tell the OS if a program tries to access a page that actually does not exist. So PHK, he looked at all this and he figured, okay, why duplicate the work? Right, we'll throw out all the memory management logic from Squid, and instead we'll use the OS paging mechanism to make sure this stuff loads fast. And he's got this history of writing some notorious emails, and he laid out the architecture of Varnish, this 2006 essay, in which he said that he wanted to bring a 1975 style program, Squid, to 2006 style architecture. So he basically said, okay, just let the OS do the hard memory stuff. And Varnish ended up way outperforming Squid for reverse proxy caching. Squid has gotten better since then, but it's basically too late. Like I don't know of anyone who actually runs Squid these days. It's basically all Varnish. All of Fastly, CDN for instance, is powered by Varnish. All right, so fast forward to roughly 2008, 2009, and we see the new hot database on the market. It's MongoDB. Okay, so MongoDB was built by a company called Tangent. Actually, no, that's not quite right. It was a component in a set of tools that was yanked from a company called ShopWiki. So ShopWiki has one of the most dastardly clever business models that I've ever come across, which is, I'm not sure if they still exist, but like what they used to do is they would buy up misspelled domains, and then when you went to one of these misspelled domains, they could generate an online store like right on the fly based off of some keywords that they extract from the domains. But I'm curious if basically browser domain autocomplete like just killed this company off. But they had this great web development platform, which included a database, right? And they thought, okay, let's spin off this web dev platform into entirely separate companies. So that's Tangent. After some problems trying to sell the entire platform, Tangent discovered actually that the database was immensely popular, and it was the only part of the platform that had real consistent usage. So they focused just on that. And so a couple of years ago, they made the transition sort of symbolically complete by renaming their company to MongoDB. So just a note, for the rest of this talk, I'm focusing on Mongo pre-version 3. So the things that I mentioned here are all things that Mongo no longer cares about. They've solved a lot of these issues. All right. So Mongo is a document store. Actually, I'm curious, how many people have used Mongo? Okay, so quite a few, like at least half. Okay, so it's a document store, which under their definition is basically it's JSON objects with unique IDs plus some secondary index functionality. So this comes from their documentation. This is a document that you put into the database. It has a unique ID, which is the _ID field, and then everything else is schemaless. It's a pretty free form. So really, the key part here is that Mongo really thought of themselves as a fancy key value store, right? The key being the _ID and the document itself being the value. And so the design of that meant that, for instance, things like secondary indexes actually lagged behind the primary index slightly. And they did things like they bolted on a MapReduce framework. And then they replaced that with an aggregation framework, and then they added sharding. But none of this work really came from an initial sort of cohesive theoretical design. It was things that they thought the market was asking for and was useful in the market. SQL, in contrast, was theoretically defined in the 70s, and then had a decade of experimentation before it reached Postgres, and then another decade before it reached MySQL. So there's a very big difference in like the speed of the development of the of the ideas in these two systems. So Mongo they latched onto the big data movement, and at this time it was not really a thing that was parodied. It was like a real thing, right? And they got this name Mongo from the word humongous, right? And they implemented a memory management model a lot like the one that we see in Varnish, right? And in fact, I wasn't able to verify this, but I believe even in their documentation somewhere they linked to the Varnish docs. So they made the same argument that modern OS memory management is better than manually handling memory in the application. Okay, so So it turns out for key value stores like Varnish, the algorithm the OS uses to efficiently handle this page movement is something called least recently used. And this actually works pretty well in practice. So the question is, okay, when the OS has to move a page from disk into RAM and then move a page from RAM out to disk, how does it pick which page in RAM to eject? So this algorithm says, okay, order all the pages by the last time that they were accessed and eject the one that was accessed the longest ago. So in other words, keep pages in RAM that look like they keep getting accessed. So this is generally very good for Varnish. So web pages most recently accessed are likely to be accessed again. And for Mongo, as a KV store, it's probably good as well, right? The documents most recently looked up will probably be looked up again. Okay, well, why is it bad for Mongo? So for secondary indexes, so scanning across a range of documents, or looking up data not on recency, LRU turns out to actually be a bad thing. So Michael Stonebreaker in 1981 argued, and also in subsequent work in the 80s by Chow and DeWitt, they show that manually managing memory and disk accesses gives better performance than letting the OS take care of it. So just a side note, Michael Stonebreaker is the grandfather of database implementations. His team developed the architecture, not just for modern SQL, but also for column stores like Vertica and Redshift, and now memory optimized systems like VoltDB. Why is LRU bad for secondary indexes? Okay, so this is the intuition. So on a secondary index lookup, right? So your documents are usually not ordered by last time access. They're ordered by some property of the document that is independent of the time that the document was accessed. So here's an example. So suppose that you have this collection of documents that contains website user information, right? So for instance, you've got these 4 users here. The ... actually is supposed to represent lots and lots of other users, but I'm just showing these. And the different colors represent different pages. So ID 1000 and 1001 are in the same chunks of memory. And 999 is in a different chunk, right? But all of the things, if there were more things that were blue, they would all be in the same chunks. So don't forget too that chunks of memory are pulled in fixed size pages one at a time. Okay, so the ID increases on every new user. So new documents are ordered in the pages in the order in which users sign up. But suppose that we have a page in which we like to list all of the users, right? And so we want to show, let's say, the first 100 users alphabetically. So what we do is we build a secondary index on the username, and then we do a range query ordered by the username, and we limit that to 100. So under the naive let memory handle its strategy, we look up Alice first, and that would pull in the entire green page, then Bob, that would pull in the entire blue page. Which, that doesn't sound so bad, but what happens if another request comes in right at this instance and the OS decides to switch and the OS decides to switch to that one and give it a bit of CPU time? So it's possible, sorry, I'm losing all of my notes. So it's possible that this process will need some memory and that the OS will have to evict a page from RAM and then send that to disk. So if it uses LRU, then, and the green page is the oldest page, it'll move that into disk. So then let's say that we switch back to the original request, right? And we have to look up the contents of Carol. So this brings the green items back into memory. And so this moving of stuff to and from disk is really expensive, right? It's four orders of magnitude slower than just trying to access memory. So even if it doesn't happen very often, when it does happen, it's very expensive. But not all is lost. With some effort, the database can actually be smart about tracking this location of these documents. And it can figure out, okay, I know 2 of my objects are Alice and Carol, and they're in the same page. So when I look up Alice, I should also go ahead and look up Carol. And then I can look up Bob and sort the results in memory later, right? What's more is if the database can guess that it'll need blue right after green, then it can fetch green, start sorting green in memory, and then at the same time, fetch blue. So Notably, this kind of prefetching behavior is something that only the application has a shot at predicting, right? So the OS understands nothing about the contents of the green and blue pages. So MongoDB, they decided to believe PHK and not Stonebreaker, which is a technical mistake. And that's because Mongo thought of itself as a KV store, not as a database. Okay, and then Foursquare. There was an infamous Foursquare outage in 2010, and it was epic, and extreme kudos to Mongo and to Foursquare for being so public about it. I mean, it sounds like I'm really complaining about Mongo quite a bit, but I consider this postmortem to be one of the most important things for modern web developers to read. So Foursquare went dark for 11 hours, and it's because one of their Mongo databases exceeded the amount of RAM that was available on the machine. So the OS paging mechanism started to cause performance issues. And that made a huge subset of queries very slow. So Foursquare, they figured this out. And then they brought up a new Mongo instance and started to migrate some of this data off to, in some attempt to alleviate the pressure on the main database. Makes sense, right? To their surprise, it didn't actually help. So why is that? It's a Swiss cheese problem. In the postmortem, Mongo explained that this was because of the memory allocation strategy. So as documents moved off one server into another, Mongo would free that small chunk of memory. But because all these documents were slightly different sizes, not much of the memory actually became free and reused. And so we saw this with the Swiss cheese pattern in the memory allocator. So not just that, but the OS paging mechanism brings an entire page in and out of memory regardless of how much of that page is actually being used. So even if all but one of the documents in the page gets migrated off, right, as soon as the database needs that one last straggler, the entire page comes back in, right? And so the bytes required to bytes loaded ratio is very low. Mongo itself might know which pages are not being used efficiently and be able to do something. But at the time, they were using a memory allocator that actually behaved a lot like just standard memory allocation, and then they let the OS handle the pages. So Mongo did not have the capability to do this. So don't forget, right? So smart behavior depends on the application logic, and the standard allocators don't have that logic or that knowledge. So the fix for this problem was essentially to rewrite all of the documents in place, and thereby removing all of the empty space. If you're a Java person, this looks a lot like stop and copy garbage collection, which is what happens in your Eden space. Okay, so there's some irony in this because Mongo was marketed as being able to handle huge amounts of data, right? But more accurately, it could handle a lot of KV lookups. And so this was a case where the memory architecture chosen for performance and scale reasons was precisely why it failed. Right, so I'll quickly contrast this to a system like Postgres, right? So Postgres does two things that are relevant here. The first is that it manages the pages very carefully, and on a query, on a secondary index, it plans out the sequence that it's going to fetch the pages off disk. And then the second thing is that every row in Postgres is the same size in bytes. Right, so this is a direct consequence of having a well-defined schema. So that points example I gave, like in the flight simulator, you can imagine it's easy to write a special optimized allocator if you know that every request is going to be for the same size. But poor Mongo is schemaless, and so every record could be a different size. All right. So let's end the technical part of this talk and dive into some ethics. Okay. So it's unfair to expect that Mongo really knows what your usage pattern is, and it's actually in general it's a very hard problem to be able to define one model that works for most applications. My beef with all of this has to do with the marketing around the project. So I think there are a couple of things in play here. So the first is that Mongo transitioned from a dog-fooded database into a VC-backed venture. Right. The second thing is that data is inertia. The third thing is that 10gen didn't have any big data use cases. So the incentive structures for VC-backed companies are to go big or bust, right? So and there's also this general trend. I'm sure you've seen all of this in your companies that you adopt tech that's open source, And then maybe you adopt tech that's free but closed source, and then maybe you pay for stuff that's closed source. So Stonebreaker looked at this, and he argues this about all new database projects, VoltDB included, which is that a database vendor, the only way that they can really stay in business these days is if they offer their software for free as in beer at least, to accumulate a wide base of users, and then they monetize a small number of those users. So point number one means that Mongo's strategy, right, is to make the thing popular, not to design it well. So why wouldn't you just switch off of Mongo, right? Because of point number two, it's really hard, right? So by the time you're at scale and you see cracks in the design, you've adopted an entirely unique data model, right? So no other database quite matches Mongo, unlike SQL, for which there are multiple competing systems, and you have a lot of, and you have a lot of options, right? So it's really hard to migrate not only the data, but to also port your application. So there's in effect a kind of data lock-in, even though Mongo itself is free as in freedom. Data is inertia. So early adoption plus vendor lock-in means growth numbers look good, and that's what VCs want. And the third thing is that Mongo stopped getting dog-fooded, and as a result, something like the Foursquare outage happens. I mean, like if you think about what actually happened here, right? Foursquare responded to a full database by adding another node, which is exactly a completely reasonable and expected thing to do, right? And then they lost their cluster for 11 hours, right? Undoubtedly, Tengen had tests on bringing up extra nodes, right? But they somehow missed out on this very real-world failure case. But what about the ethics of consumers like you and me? Right? Our tendency is to use free as in beer stuff and then grab software and not pay is what actually drives software vendors to VC growth models. Right? So there's a similar thing going on with media. Right? So the tendency to read only free content drives publishers towards advertising models. Like they want lots of eyeballs and then they'll monetize a small set. And and it just kind of aligns the business in weird ways. Right? So as a consumer, you want to make sure that you're paying for quality in some way. I'm sorry, that you're paying your vendor in some way that encourages quality. Right? So free content incentivizes lots of eyeballs with low conversion rates. It also encourages freemium models, right? So which I think for a database system is incredibly problematic. The popular strategy is, okay, what features would a big company pay for? So let's say like multi-data center replication, and let's charge for those features, right? But there's a small set of companies that need that too. There are small companies that need that as well, right? So withholding that feature is kind of like saying, nice data you got there, would be a shame if something happened to it. Then there's convenience. So I think Stonebreaker misses this point. So it's not just that the software is free, but that the software is convenient. And I think we have a tendency as software engineers and just maybe in general on the internet to really go for convenience, right? And so we figure we'll move fast and then we'll work things out later. Developers, like for instance, are accustomed to downloading installation scripts and piping them directly into a shell. I mean, like how lazy do you have to be just to allow anybody, right, to have pseudo access to your machine? And there's this weird dev culture of laziness being a virtue. So for instance, Larry Wall, the creator of Perl, he says is one of 3 virtues of programmers. And really taken without nuance, I think that's kind of a horrendous virtue. And finally, I think we as software developers, we have to be okay talking about failure. So I'm particularly thinking about failure of our own systems, right? The Foursquare postmortem is great. Like these kinds of postmortems are becoming more common, but I don't think that they really go into the amount of technical depth that they should. And I think that we have an ethical responsibility to be more open about our failures. All right, so I'll end with this guy. This is Richard Fineman. So science is about failure, and he talks about how the core of the scientific method is the ability and the responsibility to actively try to disprove your own ideas, not just those of others. Right? So Fineman says, so he talks about the difference between science and advertising by illustrating a Western oil advertisement, right, which claims that their oil doesn't soak through food. So Fineman points out, yes, this is indeed true, but actually no oils soak through food evaporated at a certain temperature. So evaporated at a different temperature, all oils soak through food. So he says that's the difference between marketing and engineering. So the marketer says our database is designed for big data. That's technically true, but the engineer should say we've never tested it beyond X. Right? Fineman, he talks about a civilization in the South Seas that became accustomed to receiving supplies from Western nations during wartime. Then when the war stopped and the planes stopped coming, they participated in rituals in some attempt to get those planes to come back. Right? So they made fake headphones with fake sticks, and they went out to empty landing strips, and they made like all of the motions of landing crews, thinking like that's the thing that got the planes to come. And Fineman calls this cargo cult science. Right? It's the motion or participation in what's seemingly science, but really lacks something fundamental. And he talks a bit about the history of the oil drop experiment, where scientists would throw out their replications if it didn't match the previous results. But it turns out that the very first experiment was wrong. And it took decades for us to get the charge of an electron correct, because we kept throwing out all the results that didn't match and kept the ones that did. So the scientific community talks openly about problems with incentive structures encouraging bad science. The system is incentivized to produce positive results, like through publishing, journals, getting accepted into conferences, but real progress actually depends as much on negative results as it does from positive results. But the system is rigged really in favor of those who produce positive results. So I think in a way we're in a golden age of cargo cult open source. Like we have these communities that are largely driven by incentive schemes which distort open source community-driven development. And acknowledging this is happening, I think, is the first step towards fixing it. But even science hasn't science doesn't have it figured out either. So I think as devs of open source and as users of open source, like we have to be honest that our actions may actually be distorting the true process of open source. So Fineman says the first principle of eliminating cargo cult science is that you must not fool yourself. Right? He also talks about a second principle, which he doesn't actually enumerate in his essay, but he says that as a scientist, you need to have the integrity to bend over backwards, to give all the information, right, to explain how you might be wrong and how your data may point to a different conclusion and how your experiment fails. So he says the first principle is to not fool yourself. And I will add that the second principle is not to fool others. So as developers, we should first have to not fool ourselves, and then we can't fool others. So I think if you write code for a living, closed or open, you should ask, okay, am I allowed to be honest? Can I provide the information total and complete about how my system works well and poorly? When was the last time that you went to an open source project to their landing page and saw links to blog posts about how it failed? Right? Like there's no shame in linking to failure. Like it makes the project stronger and it gives engineers something to solve. And there's a third principle that I've been thinking about as well, which cross-cuts a bit with the computational social science that I do at Cortico and in the media lab. So recently I came across work by Liliana Mason, who's a political scientist at the University of Maryland, College Park. She talks about polarization and identity politics. And she argues that politics becomes contentious when technocratic ideas become intertwined with the person's identity. So if your identity is indistinguishable from, for instance, guns or transgenderism, then a technical debate about gun policy or about the definition of gender becomes an attack on your identity. For open source developers, especially project founders, the software is a part of their identity. And I think some of this is true for single companies as well, like Mongo. I mean, like Mongo renamed itself Mongo. So we should aim to criticize ideas and not people, but this becomes difficult if the idea itself is tied up in the people and like in the identity. Mongo was never really a community. It was never really community run to the same extent that, say, Python is. So even though Python up until recently had a BDFL, the project set up this PEP process that focused on the debate of ideas and not on identities. The entire conceit of the Apache Foundation is to move a project from its founders into a sustainable community. The 0MQ C4 process is one that prioritizes empowering the community over centralized control. So I suspect that an idea-oriented governance structure is something that, as consumers, we should look for and something that project founders should aspire to create. And I think an engineering org should strive to have an idea, to have this idea-oriented governance structure as well. So if an engineer's identity is tied closely to a subsystem, then the failure of that system becomes an attack on that individual. And I found in my own work, it's harder for me to admit my failures, to have integrity if I'm the only committer. But if I have co-committers, it's a team effort, and it's about the integrity of the code, and we work through the technical issues. And it's not my personal pride that's hurt when something breaks. Okay, so I'll end this talk in the same way that Fineman ended his. He said, I wish to you the good luck to be somewhere where you are free to maintain the kind of integrity I've described, and where you do not feel forced by a need to maintain your position in the organization or financial support or so on to lose your integrity. May you have that freedom. Thanks. Are you a Mongo employee?
No.
Okay.
I know a few though. So you mentioned, what was it, 0MQ and Apache and the Python project structure. Is there any sort of gold standard? Is there anyone you can point to that say, yep, this is how we should do it? Ooh. Or they're doing it better than the rest? Yeah,
that's a great question. I don't personally know. I mean, I'm like trying to figure this out. I'm doing some sort of personal exploration here, but I mean, I think I really like the C4 ideals in the process quite a bit, but I don't know of really any other major projects that use it except for 0MQ. So in my mind, it's very philosophically clean and pure, but possibly untested. Apache, of course, is Apache, right? There's clear success there. But I don't know. From the outside, like I also feel like Apache's a bit. They'll just let any project in, like as long as there's a community governance structure, right? And so as a consumer of Apache stuff, it becomes quite confusing. So yeah, the short answer is I don't really have a great idea of what's the optimal process.
And is there any way that like a improperly managed, let's say, project could transition to a properly managed one? I'm thinking specifically of like what happened with BSD last year, or maybe it was earlier this year, where a bunch of my friends that were really into it got really upset and stopped being involved with the project because of a change in their code of conduct.
Oh, what happened there?
I just don't want to get into it.
Okay, all right. I think it's possible. I mean, a lot of these projects had, 0MQ is a good example, right? So 0MQ had more of like a centralized control structure going for it, and then if I'm recalling the story correctly, there was actually like essentially a revolt, and there was a fork of the project, or not quite a fork, but like a reimplementation of something. And at that point, they decided to go with the C4 process. And one, like the key feature of C4 is that they prioritize anybody being able to commit and merge into master over like a more sort of a structured process by which you like go through testing and things, with the idea that if you can merge in quickly, you can fix things quickly. And what they noticed was that when they put the C4 process in, developers were much more engaged, they contributed a lot more code, and there was a much larger number of devs as well. And their claim too is that the quality of the software went up. I'm not sure how they measured that, but like I would just trust them. Right.
Thank you.
Yep. Yep.
Thanks for the talk. This might be a tangent. What is your opinion about the Linux kernel and this idea of identity being intertwined with the, well, in this case, it's like the identity of the person is closely related to the quality of the software over like multiple decades, and then he had to take a sabbatical, and the code of conduct changed. But it's kind of like if he wasn't that person who kind of didn't reinforce those rules, maybe you wouldn't have the Linux kernel, right? Right.
Yeah. That's a great question. So I think there are clearly some problematic things about Linus Torvalds' personality, right, which he's working through, and have been like known publicly for a while. As far as like participation and structure of the actual source code, though, I think Linus I shouldn't say that he like really like removed his identity from the project, but it was definitely like, you know, for a long time, for instance, he's had a set of lieutenants, right? And he'll offload a lot of like things like maintaining stable branches to other people. So I think he recognized at some point that it really the way that he ran the project, he would have to be able to accept a lot more contributions, right, and run it more like a community, ignoring personality problems, sort of driving people away from, you know, from the community. Yeah.